Have you ever wondered what happens the moment you open a browser, type in a website URL, and press enter? How exactly does a web page get moved from the server to your screen, step by step? Behind this process lies a complex yet highly efficient collaboration involving DNS, HTTP, caching, rendering, JavaScript execution, and more. In today's video, we're going to dive deep into the complete process of how a browser loads a web page. When you enter a website's URL in the address bar and hit enter, the browser starts a series of actions. First, it parses the URL. Parsing the URL is a crucial step in the web page loading process. The main goal is to extract key information from the entered address, such as the protocol, hostname, port, and path. A standard URL typically includes the protocol, username, domain name, port, path, file name, query parameters, and fragment identifiers. After parsing the URL, the browser checks the cache. It first looks to see if there's a cached DNS record or page content that can be reused. The cache checking process is not a single step. It follows a fast to slow, near to far strategy, checking multiple cache layers in order until a usable resource is found or it determines a fresh request is needed. This involves memory cache, disk cache, service worker cache, and push cache. If nothing is cached, the browser initiates DNS resolution, a process that goes through local DNS caches, the operating system, the router, and eventually the DNS server. The role of DNS is to translate human-readable domain names into IP addresses that computers can use to communicate. DNS resolution uses a combination of recursive and iterative queries, progressing layer by layer from the local system to root DNS servers, and eventually obtaining the IP address. First, the browser checks the system's hosts file for direct mapping between domain and IP. If none is found, it sends a request to the local DNS server. This is a recursive query, meaning the server is responsible for either returning a result or an error. The local DNS server checks its cache. If it has the IP, it returns it. If not, it proceeds to an iterative query. It asks the root DNS server, which doesn't hold the exact IP, but returns the address of the corresponding top-level domain server. Then it queries the TLD server, which points to the authoritative DNS server, the one configured when the domain was registered. Finally, the authoritative server returns the actual IP address. The local DNS server caches it and returns it to the browser, which also stores it for future use. Once the browser has the server's IP address, it uses the TCP protocol to establish a connection. TCP is a connection-oriented and reliable transport protocol, ensuring stable transmission of data like HTTP. A TCP connection is established using the three-way handshake to confirm both sides can send and receive data properly. First handshake, the browser sends a SYN packet to request a connection and enters the SYN_sent state. Second handshake, the server responds with a SYN ACK packet and enters the SYN_RCVD state. Third handshake, the browser sends an ACK back. Both sides enter the established state. The connection is now open. This design helps prevent stale SYN packets from delayed network traffic, from creating invalid connections and wasting resources. If the protocol is HTTPS, the connection also involves a TLS handshake to exchange keys and verify certificates. Once the connection is established, the browser sends an HTTP request. This is the command that tells the server what resource the browser needs. An HTTP request consists of three parts: the request line, request headers, and optionally, the request body. The request line includes the HTTP method, the request URI, and the HTTP version. The headers are key value pairs that pass additional info to the server, like host, user agent, accept, cookie, etc. The body is only included in methods like post or put and contains data to send to the server. It is separated from the headers by a blank line. After preparing the HTTP request, the browser sends it to the target web server, often passing through intermediary layers like proxies, firewalls, and CDNs. Proxies act as intermediaries. A forward proxy is client-side and can hide the user's IP. A reverse proxy is server-side and hides server architecture. Firewalls protect the network by filtering requests based on security rules. They can operate on the network or application layer. CDNs, content delivery networks, are distributed edge node networks designed to deliver resources from nearby locations, reducing latency. Once the web server receives the HTTP request, it begins the response phase, processing the request, running business logic, generating the response data, and sending it back. The server's response is also wrapped in an HTTP response message, which includes status line, HTTP version, status code, and status phrase. Response headers, for example, content type, cache control. Response body, which contains the actual data, HTML, CSS, JSON, downloads, etc. Now the browser has received the HTML and other resources. The next stage is rendering, converting the raw text into a visual page. The rendering process includes four main stages: parsing, layout, painting, compositing. In the parsing phase, The browser constructs the DOM tree from HTML and the CSSOM tree from CS. These trees are essential for visual rendering. The layout phase calculates the exact position and size of each element. This step combines the DOM and CSSOM to create a render tree. The painting phase converts layout information into pixels. The compositing phase assembles all the painted layers into one final screen image, done by the GPU for maximum efficiency. If only one layer changes, the browser can repaint just that layer and recomposite, avoiding full page re-rendering. This layer-based optimization is key to modern browser performance. During all this, JavaScript and other resources play a major role. JavaScript can directly modify the DOM CSOM rendering, making it performance critical. The rendering main thread in browsers is single-threaded. When encountering a script tag, parsing must pause to execute JS, since JS might change the structure. The async and defer attributes control how external JS is loaded and executed. Async, load and execute immediately, suitable for independent scripts. Defer, load in background, execute after HTML parsing, suitable for DOM-dependent or order-sensitive scripts. In real-world development, defer is often preferred for business logic and component libraries, ensuring DOM is ready and execution order is preserved. In modern practice, nearly all external scripts should be loaded asynchronously to avoid blocking. This is a basic optimization for faster page loads, and that brings us full circle. From the moment you type a URL, the browser begins a relay race with the server, resolving DNS, establishing connections, sending requests, receiving HTML, building DOM, CSSOM, render trees, executing JS, loading resources, all leading to the final visual page. So next time you open a web page, maybe you'll have a bit more respect, because your browser is silently performing an intricate, elegant backstage operation just for you. If you found today's video helpful, don't forget to like, subscribe, and share. See you in the next video.